Hi, this is Algebra 2, Lesson 35. We're going to talk about angles and polygons, inscribed quadrilaterals, and fractional exponents. We're starting on page 158. Okay, we're going to spend a lot of this chapter looking at your book. So if you find page 158 in your book, we remember that the sum of interior angles of any triangle is 180 degrees. Any quadrilateral, and remember quad means four and lateral means side, so a quadrilateral has four sides. Any quadrilateral can be triangulated or divided into triangles from any vertex into two triangles. So if we start at this vertex, at this vertex, and remember a vertex is just a corner. So if we start at this vertex and go to the opposite vertex, we have this triangle and this triangle. Since the interior angles of this triangle have to be 180 and the angles of this triangle have to be 180, the interior angles of a quadrilateral have to be 360 degrees. You can do this to any quadrilateral, whether it's a regular quadrilateral or not. Okay? A pentagon has 5 sides. It can be triangulated from any vertex into 3 triangles. So we go from this corner to this corner, and from the same corner to this corner. And now we have 3 triangles. Because this is 180 plus 180 plus 180, the sum of the interior angles of any pentagon is 540 degrees. Every time we add another side to a polygon, we can draw another triangle. On page 159 over here, let me move my book down just a little bit, so that'll take care of the shadow. Okay? So here we have a hexagon, a polygon with 6 sides. And it can be divided into 4 triangles. Here's 1, 2, 3, and 4. If we make a list, we can see a pattern that will show us the formula for determining the sum of the measures of interior angles for any polygon. If a polygon has 3 sides, so it's a triangle, it contains 1 triangle times 180 degrees, which equals 180 degrees. Okay, that was simple enough. If we have a quadrilateral, so the polygon has 4 sides, we can divide it into 2 triangles. 2 triangles times 180 degrees equals 360 degrees. So all the interior angles of a quadrilateral add up to 360 degrees. If we have a 5-sided pentagon, we can divide it into 3 triangles at 180 degrees each. 3 times 180 degrees is 540 degrees. If we have a 6-sided hexagon, we can divide it into 4 triangles at 180 degrees each. 4 times 180 degrees is 720 degrees. So as you see, the number of triangles in the shape that we can divide out of it, triangulate out of it, is 2 less than the number of sides. The other 2 sides of any given polygon are the outsides of the angle. So if we go back and look at this picture again, we've got this outside line is helping make this triangle, and this outside line is helping make this triangle. So these 2 corners are not being bisected, but they are being used. So we've got a triangle from this corner to this corner, a triangle from this corner to this one, a triangle from this corner to this corner, and a triangle from this corner to this corner. Right? So that's 6 sides, 4 triangles. So the sum of the measure of the interior angles of any polygon of n sides is n minus 2 times 180 degrees. So it's the number of sides minus 2. We have 6 sides, but only 4 triangles, or 5 sides and 3 triangles, 4 sides and 2 triangles, or 3 sides and 1 triangle. So the number of sides minus 2 times 180 degrees tells you how many degrees are on the interior angles of the polygon. The sum of the measure of the exterior angles of any polygon is 360 degrees, and it doesn't matter how many sides the polygon has. So we're going to go back to our book again. Okay, so here's a picture of a polygon. In this case, it's a pentagon. And they have pulled out exterior angles. So they extended some lines and made exterior angles. Okay, so this angle A's exterior angle is 75 degrees. Angle B's exterior angle is 100 degrees. Angle C's exterior angle is 30. Angle D's exterior angle is 40. And angle E's exterior angle is 115. Katie, can you get me a minifig? Really fast?
Sure. Here.
Perfect.
Go ahead, Mom.
Okay, so that's the same as this guy stood in this place and he turned all the way around because he's going to end up in the exact same place pointing in the exact same direction. All the way around a circle is 360 degrees. So for any polygon, if he walked all the way around, he will have turned 360 degrees. Now that's not talking about the distance he walked. We're only talking about the adding up of the angles that he turned. So in this one he turns 75 degrees, and then he turns 100 degrees, and then he goes another 30 degrees, and then 40 degrees, and then back to 115 degrees, and we're right back where we started. Okay? So the measure of the exterior angles of any polygon is 360 degrees. What's this minifig's name?
Spencer.
Thank you, Spencer. Okay, so for our next example, we're going to find x and y. So here we have a 1, 2, 3, 4, 5, 6 hexagon. It has 6 sides. And they would like us to find x and y. Okay? X is an exterior angle, and all of the angles that they have given us are exterior angles. So let's start with that. So to find x, we're going to do x plus 55 plus 80 plus 40 plus 50 plus 65 plus x is going to equal 360 degrees. Okay. So we have x plus 55, sorry, plus 80 plus 40 plus 50 plus 65 plus x equals 360. Okay? If we pull out our calculator, we're going to get, here are 2 x's, so we've got 2 x's plus 290, because I already punched it in, equals 360. Subtract 290 from both sides, and 2x equals 70. So x equals 35 degrees. Okay, looking back at our book, that takes care of x. Now we need to figure out what y is. Y looks like a right triangle, but we can't assume that. What we do know is that it's a supplementary angle to x plus 55, because this angle plus this angle leaves us on the same transversal. So x plus 55 plus 90 is going to equal 180. And we know that x equals 35. So x plus 55 plus y equals 180. And we can substitute 35 for x. $35 plus 55 is 90. So 90 plus y equals 180. Subtract 90 from both sides. And y does indeed equal 90 degrees. But we can't assume that. We have to work it out. Okay? Let's move on. Inscribed quadrilaterals. Let's look at page 160. If a quadrilateral is inscribed in a circle, so here is a quadrilateral inscribed in a circle. Okay? Here's one up here also. The sum of the measure of any pair of opposite angles is 180 degrees. So in this case, that means that angle A plus angle C equals 180 degrees. And angle D plus angle B equals 180 degrees. We can show that by cutting this quadrilateral in half. So if we only looked at this half of this quadrilateral, we get something that looks like this. We have an inscribed angle A with chords that go from A to B, and A to D, and it inscribes arc C, right? We also have this side of the quadrilateral, which is inscribed angle C with chords from B to C and C to D, and this arc that's A. The measure of any inscribed angle is half the measure of the intercepted arc, right? So that means, let me bring my page up here. So that means that angle A is half of the arc BCD, and angle C is half of the arc BAD, and BCD plus BAD equals 360. BCD plus BAD, these arcs put together equal the whole triangle. So that's 360 degrees. Okay, so if we take half of this 360 degrees, we get 180 degrees. So, and then if you take half of this, you also have to take half of this and half of this. Okay, so we have 1/2 of the arc BCD plus 1/2 of the arc BAD, and that equals 1/2 of the 360, which is 180. Okay, so half of BCD is angle A. Half of arc BAD is angle C. So if half BCD, we can rewrite that as angle A, and half of BAD we can rewrite as angle C equals 180 degrees. Then we can see that these two opposite angles equal 180 degrees. We can do that with any quadrilateral and prove that the opposite angles equal 180 degrees. Okay? Now that we've proved that, we don't have to do it again, as long as you remember that the opposite angles in a quadrilateral that are inscribed in a circle equal 180 degrees. Okay? Okay, so here we have this quadrilateral inscribed a circle, and the book wants us to find X, Y, and Z. here's x degrees, here's y degrees, here's 80 degrees, 70 degrees, and this little arc right here is 50 degrees. Z is this arc from here to here. So because the sums of the opposite angles in an inscribed polygon equal 180 degrees, that means 80 plus x have to equal 180 degrees, and 75 plus y have to equal 180 degrees. So that's an easy place to start. And say 80 plus x degrees equals 180, and 75 plus y equals 180. Subtract 80 from both sides, and x equals 100 degrees. Subtract 75 from both sides, and y equals 105 degrees. Because the measure of an inscribed angle is half the measure of its intercepted arc, we can see the 80-degree angle here actually inscribes from this point to this point, which is 50 plus z. So 80 degrees is going to equal 1/2 of 50 plus z. Because that's the arc from here to here, which is what the angle 80 degrees inscribes. So if 80 degrees equals 1/2 50 plus z, 1/2 of 50 is 25 plus 1/2 z. Subtract 25 from both sides, and we get 55 equals 1/2 of z. We're going to multiply both sides times 2 to get rid of that denominator. And z equals 55 times 2, which is 110. Take your time, work through the steps. Okay, let's move on. Fractional exponents. There are two ways to write the square root of 2. We can do it this way, or we can do it this way. Okay? This is not a property. It's not an inherent property of two squares. It's a rule. Somebody decided that these are two ways we can write the square root of 2. Okay? 2 to 1/2 equals the square root of 2. 2 1/3 equals the cubed root of 2. 2 to the 4th equals the 4th root of 2. And so forth and so on. Both the product theorem and the power theorem apply to fractional exponents. So if we have x to the 5/3 times x to the 8/3, we can solve this by adding the exponents together. So we'll have x to the 13/3, because the 13 is the 5 plus 8. That actually equals x to the 13 cubed. That's the same thing. Okay? So let's do some simplifying. We have 4 to the negative 1/2. Okay, so 4 to the negative 1/2 is the same as 1 over 4 to the 1/2, which is another way of saying 1 over the square root of 4. The square root of 4 is 2, so this actually equals 1/2. Okay, here's another one. Negative 27 to the negative 1/3. Okay, do not you lose this negative. That negative needs to be calculated into your problem. So negative 27 to the negative 1/3 equals, if we deal with this negative first, it's going to equal negative 27, 1 over negative 1 over 27 to the 1/3, which is the same as the cubed root of 27, which is the same as minus, the cubed root of 27 is 3, so it's minus 1/3. Okay? We aren't taking the cube root of negative 27 unless the negative 27 had been in parentheses. Okay? Alright, here's another one. Simplify 16 to the 3/2. Okay, we can do this two different ways. We can do 16 to the 1/2 to the 3, or we can do this 16 cubed to the 1/2. You can do these in either order and you're going to come out with the same answer. So choose the way that seems easier to do to you to do, depending on the number that's being modified. In this case, we've got 16, and the square root of 16 is 4. It's easier to take the square root of 16 than it is to raise to the 3rd power. So the square root of 16 is 4, so this will be 4 cubed, and 4 cubed is 64. Okay? We're going to get the same answer this way. We just have to probably use our calculator or a piece of scratch paper to find that the 16 raised to the 3rd power is 4,096. And then we take that. We take the square root of that. And it turns out the square root of 4,096 is 64. So we're going to come out with the same answer either way, but this is easier to do without a calculator. Okay, so you're just going to look at these problems and figure out which is easier for you to do, which way it is easier to do first. If the simplified answer will leave you with a decimal, so if this had actually been 15 and 3/2, which is not going to come out in a pretty thing, in a pretty answer, we can just leave it here. That's as simplified as we can get it without using a decimal. Okay, so you could have left it at this as an answer. Because, of course, a lot of the problems are not going to come out pretty. They're going to come out looking like this. Okay, now we have simplify the opposite of 8 raised to the negative 2/3 power. So this isn't negative 8 raised to the negative 2/3 power. The negative was not in the parentheses with the 2/3 power, so it's the opposite of 8 raised to the negative 2/3 power. So we're going to leave this negative on the outside as we are doing these steps. Okay, so there are two ways, once again, that we can do this. We can do 8 squared raised to the 1/3, and we'll stick the negative there. Or, that is the same as negative 8 to the 1/3 raised to the negative 2. Either one will work. So you think about which way it's easier for you. 8 squared is 64. The cube root of 8 is 2. Okay, so whichever way your brain works best. If we do it this way, it'll be 64 to the negative 1/3. The negative here flips this, so it'll be negative 1/64 to the 1/3. The cube root of 64 is 4, so this is going to be negative 1/4. Or we can do 8 to the 1/3 is 2. So the negative square. The negative flips it over, so we have 1/2 squared, which is the same as negative 1/4. Either way works. Do it whichever way is easier for you. Okay? That is it for this lesson. Try your practice problems and your homework and let me know if you have any questions. Thanks.